Okay, welcome back. Feel a little bit frazzled today. I spent the morning reading to my daughter. I read "Is Your Mama a Llama?" to her 40 times in a row. This is really great literature if you happen to be 4 months old. Highly recommended. Anyways, whatever kept her from crying, and that was what kept her from crying. So, is your mama a llama? It is. Okay. Sorry, that digression aside. Today we're going to study Ginzburg-Landau theory. For people who've studied Landau theory of phase transitions and Ginzburg-Landau theory before, this will look a little bit familiar, but then we will extend onward to see the relationship to the Anderson-Higgs mechanism, application to superconductors, and we'll use Ginzburg-Landau theory to derive some interesting results about superconductors, which maybe even those people who've studied phase transitions might not have seen before. So to start our exploration into Ginzburg-Landau theory, we're going to start with the simple case of a neutral superfluid. And we'll write down the Ginzburg-Landau free energy, GL free energy, which is exactly the form which is exactly the form of the Gross-Pedievsky equation that we derived earlier. So it's an integral over all space. There's a spatial derivative term, gradient of psi squared, and then there will be some expansion in powers of absolute value of psi, and there may be even further terms. Oops, get myself out of the way there. Like this. So this term is psi to the fourth. This term psi squared. That's what we derived earlier, psi to the fourth term. And this combination, the terms without gradients, is often known as V, the potential, as a function of the absolute value of psi. Now, a couple things about this potential function. First of all, it's usually sufficient to truncate the series at fourth order, or at least it will be for us sufficient to truncate the series at fourth order, so we can throw away all terms of higher order. We do want V to be positive for values of, we want this to be positive and large for large psi. And for that to be true, we need alpha 4 to be greater than 0. If alpha 4 was less than 0, then V would get very negative for large psi, and the lowest energy solution would be for psi to just blow up, and we can't have that. So for stability, we want alpha 4 to be greater than 0. And furthermore, we're going to discover this coefficient, alpha 2, is going to be related to the critical temperature. It will be A times T minus critical temperature with A greater than 0. So we'll be able to show that in a moment. Finally, we're going to start by considering a uniform system, with a system with no gradients, a homogeneous uniform system. The lowest energy homogeneous uniform system can have is if there are no gradients in psi. Gradients in psi just raises the energy. So let's just drop this term, drop the gradient term, drop this to begin with. Okay? All right. So this is our free energy we want to work with. And we'll consider the case of T greater than Tc, by which I mean here the case of alpha 2 greater than 0. So let's plot what the potential looks like. Okay. So this is psi here, and this is V of psi here, and we find that it grows, well, it starts by growing quadratically at small psi, and then it at larger psi it goes up faster as the fourth power. And the minimum of the free energy, min, is of V of psi, is at psi equals 0. And that tells us that there is no condensate, that psi equals 0, no order parameter, no condensate. Okay, and That's what we had hoped. For t greater than Tc, you would have expected no condensed. On the other hand, let's consider the case of t less than Tc, by which I mean alpha 2 is less than 0, considering our relationship of alpha 2 to Tc. When t is less than Tc, alpha 2 becomes negative, in which case, let's plot the V in this case. Okay, this. There we go. And here, the function is going to start out negative quadratic, so alpha 2 is less than 0, but then it will turn around and go back up due to the alpha to the fourth term. Okay, so this is absolute psi, and this is V of psi. Okay, due to the alpha to the fourth term, the function goes back up for large psi, and the alpha squared term makes it come down for small psi. Well, it's a sort of sloppy looking quadratic curve, but you know more or less what I mean. It's symmetric. Okay. Now the minimum of this function, min here, it's easy enough to show that if the function were minimizing, maybe I'll just write this out here. If v of absolute psi is alpha 2 psi squared plus alpha 4 psi 4, the min with alpha 2 negative, alpha 2 less than 0, the minimum of v of psi occurs at absolute psi is absolute alpha 2 over 2 alpha to the 4, alpha 4. So that's a exercise in finding the minimum of a function. And so we're going to define that point to be called, that minimum point, we'll call it psi naught. I guess we'll call it psi naught, and we'll declare it to be real. Psi naught, and this point here we'll call minus psi naught. Oops. Minus psi naught. So psi naught is then this quantity, and that is then considering our definition of the order parameter earlier, this is what we're going to define to be the square root of the superfluid density. Okay, so this is standard Ginzburg-Landau theory. In Ginzburg-Landau theory, above Tc, you have something that starts out quadratic. It's always positive, and the minimum is at psi equals 0. Below Tc, you break a symmetry, and the minimum is going to be at some finite value, and that's the symmetry broken phase, which in our case is then the superfluid phase. Okay. Now I drew this in this potential V in one dimension, but really psi is complex. Psi is complex. So I should have drawn it in 3 dimensions. Let's see if I can do this a little bit better in 3 dimensions. So we have something that looks like this, and then we have a 3rd dimension like that. Okay, that's supposed to be, those are all supposed to intersect at 0. And let's see how we can do this. So the potential, the function we're trying to plot looks kind of like this. It's comes out like this. Oh boy, it comes up like this. Like that, and then turns around and comes up like this. This. Okay, so it's what is typically called a Mexican hat potential. Draw this a little better. Okay, so it's radially symmetric. It's basically taking this curve here, and just rotating it around the y-axis. So the axes here are v of psi on the vertical, v of psi on the vertical, and then real of psi on this axis, and imaginary of psi on this axis. Okay, so the v of psi, v is only a function of the absolute value of psi, so it's rotationally symmetric, or if I had drawn it correctly, it would have been rotationally symmetric around the vertical axis. Okay. This is a terrible Mexican hat potential, but I'm not going to try to draw it again because my drawing ability isn't that good. See if I can make it a little clearer. Okay, let's go straight down like this, right through the middle. Okay. Okay, so when we have a Mexican hat potential like this, we've broken a symmetry. We've chosen a particular direction for the phase of psi. So phase of psi must be chosen in the symmetry broken phase. Phase of psi is arbitrary, but you have to choose some particular phase when you break the symmetry. When you go below Tc, psi takes some non-zero value, so you have to choose some phase, but it doesn't matter what phase that you choose. Now, when you have such a situation where a continuous symmetry has been broken, you will always have a Goldstone mode, which is a low energy expect Goldstone mode, which is the mode associated low energy mode associated with re-choosing the direction that we've where we break in the direction which we break the symmetry. So for a ferromagnet, for example, when you go below Tc, if you have a Heisenberg ferromagnet where the spins can point in any direction, when you go below the critical temperature, the spins have to point in. They all point in the same direction, but they have to choose a direction to point in. Let's arbitrarily say that they point up, but there will be a low energy mode, a spin wave mode, which comes down to zero energy, associated with changing that choice of direction from up to slightly off up, so it can wiggle in its direction, and that's a low energy spin wave. Similarly here, there should be a mode associated with changing the complex phase of this order parameter, re-choosing this direction where we've broken the symmetry. We break symmetry. So in other words, we could have chosen any point around the rim of this Mexican hat, around the rim of this minimum. Any point around here could have been chosen as the ground state, and then once we choose that direction on the ground state, say we choose this direction, there's going to be a low energy mode associated with allowing this direction to wiggle. It's like a spin wave mode. So this will be a sound. This will be a sound mode, an acoustic mode, sometimes known as an acoustic mode, or a Goldstone boson mode. And I think there is a homework assignment to try to actually calculate the spectrum of this Goldstone boson mode. Okay. In order to figure out the real properties of the superfluid, we want to put the spatial dependence back into the system, and we do that by basically deriving what we call the Ginzburg-Landau equation from the free energy, and we did this before. We take the free energy and we functionally differentiate it with respect to, say, psi star of r, and we get, putting back in the spatial dependence, we get minus del squared psi plus alpha 2 psi plus 2 alpha 4 psi squared psi. So setting this equal to 0, this gives us the nonlinear Schrodinger equation that we talked about before. Schrodinger, or Ginzburg-Landau equation, Schrodinger, Ginzburg-Landau equation, or Gross-Pedievsky equation. if we had derived this from for interacting bosons. Okay, incidentally, Ginzburg-Landau theory was worked out first in the context of superconductivity, and only later was it applied to superfluids. Okay, now in a uniform system, we know, we already calculated the magnitude of psi is squared is going to be alpha 2 over 2 alpha 4. Alpha, do we get that right? No, here. So I think I got that wrong in my notes here. I wrote this as magnitude of alpha, but I think it's magnitude of alpha way back here. I think this is magnitude of psi squared should have been that. Yeah, that should have been magnitude. I was wrong in my notes. Sorry about that. I better fix that in the. I hope that's right in the typed notes. I'll check that. So alpha naught squared is absolute alpha 2, assuming alpha 2 is less than 0, in other words, in the condensed phase, divided by 2 alpha 4. And it's useful. This is sort of sets the scale of psi in the problem, and it's useful to rescale psi by psi naught. So let's define. Here we go. Let's define f equals psi over absolute psi naught. I guess psi naught is real. We're going to choose it real and positive anyway, but we'll write it as absolute psi naught. And then plug that in to our nonlinear Schrodinger equation. And what we get is, see if I can maybe make this a little smaller so you can see it all at the same time. Okay, now I have to put myself out of the way so you can still see this. So then what we have is minus h bar squared over 2m gradient squared of f plus alpha 2 f plus 2 alpha 4. Then we have psi naught squared absolute f squared times f equals 0. And now plugging in the value of psi naught squared into here, we can this combination ends up being another factor of alpha 2, which we can then factor out. So the end result then becomes, I'll write it this way, psi squared del squared f plus f minus absolute f squared f equals 0. Okay, so this is a rather important equation. It's our nonlinear Schrodinger equation in its sort of simplest form, where I've defined here, psi squared is this combination, this thing divided by alpha 2. So I'll write that out is, psi squared is h bar squared over 2m absolute alpha 2, as long as we're below Tc. Okay, so this quantity psi is known as the Ginzburg-Landau coherence length. Landau coherence length, and it's basically a it's a stiffness length of the superfluid. It's how it's the distance scale over which you can bend psi, bend the value of psi, or bend the phase of psi. That's the sort of natural length scale over which psi changes. Okay, and I'm obviously terrible at drawing these psi symbols also, but everything that looks like a squiggly is the same symbol. Okay, so I'll write that. This is the stiffness length. Stiffness length for twisting. Psi. And at low temperature for helium-4, at low T, psi can be very small. It can be about 1 angstrom, something like that. So it's twistable on very small length scales. Okay. Now, but note here that alpha 2 alpha 2 is goes to 0 at the critical temperature. And that means as you get close to the critical temperature, as T goes to Tc, psi diverges. Well, let's write it out explicitly. Psi goes as T minus Tc to the minus 1/2. Okay, even though the coherence length is very short, as you get close to the critical temperature, it will diverge. Okay, at least it grows this way, at least in Ginzburg-Landau theory. Okay, so we have this nonlinear Schrodinger equation. Let me actually copy it because we like it. I'm going to use it again. Copy and bring it down here. Use it again. Paste. Okay, this is the equation that we want to solve. It's our nonlinear Schrodinger equation. And typically nonlinear equations are very hard to solve, but there are some things we can say about it. There are various exact solutions. We can write down 1, f equals 1 everywhere. That is just the constant uniform solution where you just have uniform superfluid everywhere in space, all the way out to infinity. That's a perfectly good solution. It's maybe not that interesting, but it's a perfectly good solution of a uniform superfluid. A more interesting solution is a solution of the following form, that f equals hyperbolic tangent of x over square root of 2 times psi. So what does that look like? Let me see if I can draw that. So this looks like, again, drawing my axes. Here's x, here's 0, and here is f. And let's put, this is f equals 1 here at this line, f equals 1, 1 equals f on this line. And then we have a tangent, which starts by growing linearly and then converges to this line as a tangent. And the healing, let me see, draw that more like a tangent. A little bit more like a tangent, okay, kind of like this. Okay, and the healing length of this tangent is psi. Okay, so the properties of this, it's nice. It goes to the uniform solution at large x, but it goes to 0 at position x equals 0. So this is the uniform solution out here, and also f equals 1. I should maybe write this down. Recall that f equals 1, the uniform solution, f equals 1 implies that psi is this psi 0 parameter, which is square root of absolute alpha 2 over 2 alpha 4. And that's the uniform solution, which is the same as f equals 1 everywhere in space, the same uniform solution that we found before. That's what it converges to for large x. The tangent converges to that, but for small x, it vanishes linearly. And this is basically a particle in a box boundary condition. Oops, can't see this, can you? Again, move myself out of the way. There. Sorry about that. So what we have is a particle in a box boundary conditions where the order parameter goes to 0 at the boundary of the box. So we have a nice tangent here converging to the uniform solution in the bulk and going to 0 at the boundary. Now, the one thing I haven't shown you is that this tangent function actually satisfies this nonlinear Schrodinger equation, and that's actually a bit of an exercise in hypergeometric functions, but it's a fairly easy exercise to do. So maybe do that to entertain yourself. A third solution that we're sort of interested in is the vortex solution, the vortex structure. Vortex, unfortunately, is not fully analytically solvable, but we'll be able to say some things about it. So let's write f equals absolute f of r times e to the I theta. Okay, so that the phase wraps around some central point. So we're imagining here that we have here's our fluid in 3 dimensions, and there's some central point here, some central line, and the phase wraps by 2 pi as you go around that central line. Okay, now we know for sure that the magnitude of f of r must go to 0. F of r must go to 0 at r equals 0 because the phase is not defined at r equals 0. So that will tell us something about the limits of this function. We also suspect that f of r will go to 1 at large r, should go to the uniform solution. But we can do actually a little bit better. We can actually calculate in some amount of detail some functional form of this f, although we can't calculate it in all of its entirety, but we can get some of the details right by throwing out the appropriate forms. So let me draw roughly what we expect it to look like. So we expect it to look like something like this and something like this. Okay, so this is r on this axis, and this is f on this axis. Again, f should saturate to 1. F equals 1 along this line. So something looks like this, and then it should look like tangent also. So here it should look like f goes as well, it will have a phase e to the I theta 1 minus something, and I'll write down the answer. It's actually the leading term, correction, is actually psi squared over 2 r squared plus dot 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 dot, and then here it actually starts as e to the I theta times r. The way we find these asymptotic behaviors down here and up here is by taking appropriate limits of our equation. Here's our equation again, plus f minus f squared f equals 0. Plugging in the radial form of the Laplacian, so del squared is going to be 1 over r d by dr, r d by dr, plus I guess 1 over r squared d by d theta squared. That. And then just plugging in the form of f equals e to the I theta absolute f, and trying to figure out what the form of absolute f is. I guess if we, for large, okay, let me just write out the whole thing then. Xi squared 1 over r d by dr, r d by dr, minus 1 over r squared. That comes from this term here, minus 1 over r squared, taking d by d theta squared, times absolute f plus absolute f minus absolute f cubed equals 0. And for small r, for small radius, f is small. Small r, absolute f is small. So you can drop the quadratic term, drop this term. And for large r, the leading term is the d by dr is going to be small. The d by dr term is, for large r, we want to make a different expansion. We want to write f equals 1 minus y and expand in y. Okay, so I'm not going to do those in detail. You can work that out for yourself to find these limiting forms. Okay, so we know something about the structure of the I keep saying superconducting vortex. This is superfluid vortex. So far we're entirely neutral superfluids. no superconducting yet. I might have said superconductor a couple times, and I apologize for that. Now, finally, we get to move on to superconductors. So we want to view our superconductors as a charged superfluid. So our superconductor is a charged superfluid, i.e. a superconductor. Superconductor. And we then want to write down a appropriate Ginzburg-Landau theory for the superconductor. So f of psi is going to look extremely similar to what we had before. The only difference, okay, there's going to be two differences. One is that we are going to now have minimal coupling to the electromagnetic field, psi squared. Parenthesis like this. Okay, so the momentum term gets minimally coupled to the electromagnetic field. We're going to still have alpha 2 psi squared plus alpha 4 psi 4, and it will still be the case that alpha 2 is going to be equal to a times t minus tc with a greater than 0, and it will still be the case that alpha 4 is going to be greater than 0. Okay, so this looks entirely the same as what we had for the neutral superfluid, except for the minimal coupling to the electromagnetic field. But to be careful, we should also have the free energy of the electromagnetic field as well. So we'll write that. We know how to write the energy of the electromagnetic field. It's going to be b squared over 2 mu naught and e squared over 2 epsilon naught in SI units. And one should be a little bit more careful even that if you're really careful about it, you realize that this integral is only over the superconducting sample, whereas this integral is over all of space. So electromagnetic fields that leave the sample have to be included. Often we're going to drop the energy of the electric field, but this is just because it's not doing anything interesting for us actually. The electric field in a superconductor is 0, but so we may drop that later on. Okay, so again, analogous to the case of the neutral superfluid, below Tc, we're going to have the absolute value of psi is going to be psi naught, which will be square root of alpha 2 over 2 alpha 4, exactly as we had before, which will call the superfluid density. And here I've put stars, as we had been doing before, on the mass and the electron charge and the superfluid density, again to represent the fact that we don't know how big the elementary boson cluster is, whether it's a charge 2 boson or a charge 4 boson or charge 8 boson or charge 1 boson. We don't know that, and only the ratios of E over m are going to matter here. Although, as I mentioned, once you look at the flux quantum, then you can tell how big the charge of the boson is. So we might expect, write this down, might expect Goldstone boson associated with changing the phase of the order parameter around the rim of the Mexican hat, associated with going around the rim of the Mexican hat, exactly as we had in the case of the neutral superfluid. However, there is none. But there is none. And this rather surprising result. Maybe I should say what I mean by there is none. Superconductors Supercond have no low energy, electronic modes. So there's no electronic sound mode, no electronic sound modes, or no phonon of the electronic degrees of freedom. That's what you would expect from a Goldstone boson, a sound mode of the bosons. But in fact, superconductors don't have them. And why don't they? This is why. It's because of the Anderson-Higgs mechanism. And I think it's fair to call it Anderson-Higgs because Anderson explained this in the context of condensed matter in 1962 and Higgs in 1964. And in fact, Higgs even cites Anderson and says that in fact what Higgs was doing was just a generalization of the Anderson mechanism. Also, I guess to give fair credit, Yoichi Nambu also was very involved in developing the understanding of spontaneous symmetry breaking with a gauge field. Phil Anderson, the discoverer of the Anderson-Higgs mechanism, passed away just last week, actually, at the age of 96, and it's this particular course is probably the most prominent scientist that we mention over and over in this course is probably Landau, but it's probably not a exaggeration to say that within the condensed matter field, Anderson might have been the most influential condensed matter physicist of the 20th century. Very hard to think of anyone who's had the same kind of influence. Even Landau, maybe, although Anderson was a little bit later than Landau. Okay. We're going to work with this free energy in order to describe the Anderson-Higgs mechanism. But this is a little bit of a cheat, to use Ginzburg-Landau theory. And the reason it's a cheat is because, people usually use a Lagrangian or a Hamiltonian description. And the reason for that is because you want to be able to keep track of the dynamics of the theories as well as the static energies. If you want to, you can think of the free energy as being the Hamiltonian or negative of the Lagrangian, where you've taken all the side dot terms, all the time-dependent terms, and you've thrown them out, or you've set them equal to zero. This is almost going to work for us. Not quite. I'll tell you where we have to wave our hands a little bit and pretend we're putting back in the dynamical terms and try to understand what they would do. But I want to stick with the Ginzburg-Landau free energy because that's what we've been doing. And there's plenty of references that will go through the Higgs mechanism in the so-called abelian Higgs mechanism from the Lagrangian standpoint. So I'm going to try to do it just thinking about free energies here. Now, the key to the Higgs mechanism here is to realize that the free energy here is gauge invariant, and so you can make a gauge transformation on it. Well, we already know that the electromagnetic fields are gauge invariant. You can make a gauge transformation on the vector potential, and the electromagnetic fields stay unchanged. Here it doesn't look gauge invariant, but it is gauge invariant under simultaneous gauge transform on both the vector potential and the field psi. So the particular gauge transform that we are allowed to make is gauge transform, which leaves F or H or L, Lagrangian or the Hamiltonian invariant, is of the following form. You take psi to e to the I alpha times psi, and you take simultaneously E star A vector potential to E star A times plus gradient of alpha times H bar. So if you look up here, what's going to happen here is that the gradient here is going to hit the e to the I alpha up here, but then it's going to be corrected for by the change in A. So the combination is going to remain gauge invariant if you do both of these at the same time. Okay, now we're going to consider the case of the temperature less than the critical temperature. And in this case, we know the magnitude of psi will, at its minimum, it's called psi naught. We calculated that's absolute alpha 2 over 2 alpha 4, some positive number. This minimizes the free energy. This quantity is known as the VEV in high energy physics. That stands for vacuum expectation value. Which tells you that even in the vacuum with no excitations at all, the field psi has a finite value. So let's see if I can draw that. I've already discovered that I'm not very good at drawing anything. But okay, here's the Mexican hat here, just a part of the Mexican hat, and this minimum here is has magnitude psi naught. Now there's what we want to do is we want to describe the excitations around some point on the minimum in terms of excitations up the hill like this, which we'll call H, and excitations around the rim, which we'll call chi. Okay, so there's two different directions we can go if we're sitting at the bottom of that hill of the Mexican hat. One is to go up the hill, it's H, and the other is to go around the bottom of the hat. That's the thing we found energetic, and that had no energy. It was the Goldstone mode previously in the neutral superfluid. So here we'll write psi is psi naught plus H, both real fields. Well, psi naught is just a constant. H is a real field here. E to the I chi going around the rim. Okay. Now we then want to rewrite our free energy, or let's just rewrite V of psi in terms of psi naught and H. So we can write it out as alpha 2 psi naught plus H squared plus alpha 4 psi naught plus H to the fourth. And if we expand that out, well, we know what it's going to look like. It's going to be a bunch of constants, which we're not interested in, plus some constant C. Okay, let's call this constant C prime over here. C times H squared plus dot dot dot. It's going to be quadratic going up and down this hill. Whenever you're at a minimum, you can always expand quadratically. You know it's going to be quadratic going up and down the hill. And if you actually do this expansion, you'll discover the value of that constant C there is 2 times alpha 2. Okay, so we know that there's going to be an energy to go up and down that hill. Now the whole key to the Anderson-Higgs mechanism is the following: that if you try to go around this around the rim by changing chi, you can always gauge transform it away. That we're allowed to make this gauge transform, and we can gauge transform this psi here to get rid of any attempt to go around the edge of this rim. So preventing you from going around the rim altogether by just choosing a different gauge. So this is a rather interesting thing to do. We're going to make the gauge transformation. We're always going to work in a gauge where psi prime is e to the minus I chi times psi. So psi prime is always going to be a real valued field, psi naught plus H. So the psi is no longer a complex valued field. It's now a real, psi prime here is now a real valued field because we got rid of any fluctuations around the bottom of the rim by gauge transform. If we plug this back in, okay, at the same time we have to gauge transform A. This goes along for the ride, minus times H bar. H bar is unrelated to H, it's my bad notation. So the free energy here, if we plug in these new parameters, we can write the free energy as some constant. There'll be integral dr. Then we have a leading term, 1 over m to m star. The kinetic term, rather, h bar gradient minus I guess, E star A prime, and then it's going to be psi naught plus H quantity squared, and then the potential term, the potential going up the hill is 2 alpha 2 H squared, and then we always have the electromagnetic terms, which look the same in if we write them in terms of B and E. They'll always look like 1 over 2 mu naught B squared plus epsilon naught over 2 E squared. But it's probably good to keep in mind that B and E are written in terms of the vector potential A, but they're also gauged in varying quantities. So in particular, I guess B is the curl of A in either gauge, and E is minus gradient of A naught minus dt A vector. I probably have a minus sign wrong here, like this. In either gauge, that's acceptable. Okay. Now, writing this, expanding this out here and canceling some terms, we get the following expression. We then get the free energy is constants, which we're not interested in, plus integral over space. There's h bar squared over 2m gradient of h squared. That's the fluctuation up and down the hill, plus 2 alpha 2 h squared, plus psi naught squared e star squared over 2 m star times a prime squared, and then plus the electromagnetic terms, plus, well, okay, maybe I'll write it, del cross a prime squared over mu naught, 2 mu naught, plus, I guess, the epsilon naught over 2 minus gradient a, it's dt a vector squared. Okay? This is being a different integral, plus integral dr. Okay, good. So let's look at these terms here. This is now the fluctuation up and down the hill. This is an energetic fluctuation. No matter what you put in here, whatever normalized function you put in for h, it's going to cost you a finite amount of energy because of this term, which is a so-called mass term. Now, it's a little bit hard to see that here, but if you remember that we had dropped all of our dynamical terms in the Lagrangian or the Hamiltonian, so really there should have been a you think of h here as being an x-coordinate in the system, and there's a conjugate p-coordinate that we had dropped. This is telling you that basically you have a harmonic oscillator going up and down the hill of h, and it has a gap to create an excitation of that harmonic oscillator. The h dot term is missing from the Hamiltonian because we're working with a free energy. This gradient term tells me that if the harmonic oscillator isn't uniform in space, if each point in space is not fluctuating the same, that costs you additional energy. At any rate, the H field is massive. This is the so-called Higgs field, is massive and has a gap. Now, more interesting for us is this A prime term, A prime squared term. This is a gap for the photon, or a mass for the photon. So let me just label this term here. This is massive photon. Massive photon. So let me try to explain why it is that this term is a mass for the photon. It's similar to the case of H, that this term is telling me that any fluctuation of the electromagnetic field that I make is going to cost me a finite amount of energy. That is unlike the case of regular photons, where you can go to larger and larger and larger wavelength, and the energy drops further and further and further. So let's try to understand why that is. If we drop this mass term for the photon, then we know that, well, okay, because both terms here in the magnetic term and the electric term have derivatives, we'll have a frequency term that shows up here, which is going to be proportional to the speed of light times times the wave vector. If you insert and the key for a massless photon, if you drop this massive term here, for a massless photon, the key is if you go to very small wave vector, the frequency drops all the way down to 0. So you have a massless field because you can get energies arbitrarily low. However, if you take any field, any finite field, and you plug it into this a prime squared term over here, this will give you a finite result. It will always give you a finite energy, even at long wavelength. It will give you a finite energy when you plug it in to this a prime term. So this is for massless, and omega goes as constant, plus dot dot dot, plus probably q squared or something, is massive. Okay, so what does it mean that the photon is massive? What does it mean? What does this mean? What does this mean that we have a massive photon? What it means here is that even at long wavelength, the photon costs you energy if you're inside a superconductor. Why does that make sense? Well, let's imagine you have a photon, say a magnetic field, impinging on your superconductor. That, the magnetic field is coming in towards the superconductor. When it goes into the superconductor, its energy goes up. And it's reflected, it's like going up a hill because its energy in the superconductor is finite. Even if it's a long wavelength, low energy photon, it's then goes up this hill because energy is finite in the superconductor, and then it's reflected back out because, it has finite energy and it can't go into the superconductor because there's a gap. There's a mass gap to getting the photon into the superconductor. What this means is exactly the Meissner effect. Photons are expelled from superconductor due to their energy, due to their mass. Okay, and we've also then discovered that there is no Goldstone boson, no low energy excitation, no Goldstone boson, and the catchphrase that people always use is that the Goldstone boson has been eaten by the gauge field A, and A, the gauge field, gets massive. So Goldstone boson, Goldstone is eaten by the gauge field A, and A, having eaten, gets massive. Because when you eat, you get massive. Okay? So it's worth, just for a second, counting the degrees of freedom that we have in the problem, degrees of freedom, to make sure we haven't lost anything. And above TC, what do we have? Well, we have psi, which has 2 degrees of freedom. 2 degrees of freedom, because it's a complex field. It can oscillate in, so you can oscillate, you're sort of at the bottom of this parabola, and you can oscillate in either the real or imaginary direction. Okay, that's terrible drawing, but you know what I mean. You can either go this way or you can go that way. There's 2 degrees of freedom in the psi field. You're at the bottom of this parabolic well. The vector potential is massless, and a massless photon has 2 polarizations. You can oscillate. The electromagnetic field can oscillate in either direction perpendicular to its vector of propagation. So it's a total of 4 degrees of freedom. Total. Okay. On the other hand, we can look below TC. We have H is a massive field. That's the Higgs field, but it's real. It's 1 degree of freedom. Okay, it's a oscillation in the radial direction of this Mexican hat. Okay, A is now massive, and a massive field has 3 polarizations, 3 degrees of freedom. So like a phonon, which can be massive, you can oscillate in the direction of propagation. You can have a longitudinal as well as a transverse, as well as 2 transverse. So we can have longitudinal plus 2 transverse modes. You cannot have a longitudinal oscillation of a massless field moving at the speed of light. So here we have 1 degree of freedom in the H field, in the magnitude of the field, and 3 degrees of freedom in the gauge field. So again, we get 4 degrees of freedom total. So we haven't lost any degrees of freedom. We've just moved them around. The gauge field has eaten one of the degrees of freedom when it becomes massive. So just before we end this lecture, I guess we'll apply a Ginzburg-Landau theory to superconductors in the next lecture. But I should comment a couple things about you see an awful lot about the Higgs boson in the popular media. So the Higgs boson is the excitation up and down this Mexican hat, the massive excitations, and you often see written in the popular media that the Higgs boson gives mass to the to particles like electrons get their mass from the Higgs boson. That's not really true. What actually gives the photon mass, gives the gauge field mass, is the VEV, the vacuum expectation value. This quantity here. That's not the Higgs boson. The Higgs boson is the boson. The excitation is this H field. The excitation's up and down the hill. The VEV is what gives the particles their mass. There's another thing that you will often see in the popular media, that all mass in the universe is created by the Higgs field, or the VEV, I guess is what they mean, and that's not true either. It's only true for leptons. For protons, for example, most of the mass is contained in gluon physics, not in Higgs physics. All right, so next time we will start up on applying Ginzburg-Landau theory to superconductors and finding out a little bit about their properties. Okay, until we meet again.